not the first one. This is actually I call it example 01, but it's actually the second example, right? So what's the second example? The second example is this. Suppose I have the symmetric buckling case. So now we're going to solve it to see that why we have asymmetric buckling. Now let's consider this. There's a force P acting here. Now the objective for this problem is to determine the buckling load, or sometimes we call it buckling force, PCR, in two different modes. Of this portal frame. And we're going to start with the first one first. Consider mode 1. Buckling. In mode 1 buckling, we have the buckling shape to look like this. That means the structure buckles like this, right? And that's why I called it first mode, right? Let's just be sure. Yep. Okay. Now, if we consider this case like that, all we have to do is to carry out the structure analysis. And this is the part you shall be familiar from structure analysis. If we cut the members and look at the internal forces, the free body diagram of this member will look like this. And external force is acting on the joint between the beam and column. And just like we're going to do it here before. Right? Now, what we're going to do is to determine all the internal forces. And internal forces will be labeled by a different color. Shall we use blue? So the red color indicates the external force, and the blue indicates the internal ones. When the beam bends like this, if you look at the beam element, which is the horizontal member, the bending moment, the direction of the bending moment acting on the free body diagram of the beam should be in this direction. Would you agree? Actually, it's too much. This is the direction of the moment, correct? Otherwise, the beam will not bend that way. That makes sense?
Yeah.
Correct. Now, if the moment is like this, because here, look at the boundary condition, they are all supported by hinge. That means at both supports, there's no moment. That means this internal bending moment must be balanced by the vertical force at one of the supports. Shall we call one of the supports A and the other B? Or we could just call it A, B, C. Call this one B, and call this one C, like this. So at point A, the reaction must go vertically like this. Would you agree? That must be the shear force. Otherwise, the moment will not be balanced. Correct? So let's call this force, capital V, as a shear force. Now, in order to balance the shear force internally, the shear force at point C on the beam member must be going down. Would you agree? Otherwise, force equilibrium will not be achieved. Correct? That's the three internal actions that we have. Now, if the moment goes acting like this, you have to remember that internal forces always appears in pairs. That means there's another moment goes like this in the opposite direction, and what happens to the shear? The shear will have to go in the what? In the opposite direction in order to balance it, right? So if at one end it goes down, which is this V here, and on the other hand, it must go up. Would you agree? That's why internally they will all cancel out. Now, here comes the interesting part. If at one point it has a P and another end it has a V, what is the internal action right here? What is this one? What's this?
Should be down.
P minus V.
Yes, P minus V, right? Very good. So it should be P minus V. Now, if this P minus V, what about this one? This is also P minus V, right? If it's also P minus V, what is this one here? It's also P minus V. Correct? Now, what about the moments? If the moment goes this one like this, and that means another moment will go like this, correct? To balance it. And another moment we must acting on the column member must be in the opposite direction, which will be like this. Right? Now we're going to use this moment to determine what's the direction of the shear force acting on the column member. If you know this moment goes this way, you know already that the shear force must be acting this way. Right? Otherwise, it will not be balanced. If the shear force acting this way, you also know that another one must be acting in the opposite direction. Then we're done with the analysis of this total frame. So this is the first mode. In the second mode, then we can just repeat exactly the same procedure. The second mode looks like this. Ouch. The second mode is the opposite, which goes, gotta change it. Second mode goes like this. And let's not forget about the force, P here. Again, look at the free body diagram. Here, here, and here. Now, this time, everything will be in the opposite direction, correct? So we start with what? We start with the internal bending moment on the beam member. To make this thing bend like this, the moment must be acting like this, right? If moment is acting like this, to balance this moment, the shear force can only be going downward, correct? Now, if you know the shear force by force equilibrium, you know that at the other end, the shear force must be going upward, like this. And at the same time, the moment at the other end must be going in the opposite direction, right? And also, by force equilibrium, you know the shear force acting at the joint must be going downward. So this is the RV here. Now, because we always have this force P at here, so the same question, if I can ask you again, what is the reaction at this point? It's no longer P minus P.
P plus V?
Good. It's going to be P plus V. So it's going to be P plus V. And the rest is just routine. So this is also P plus V, this is also P plus V. And if the moment goes like this moment must go like that, and that moment must go like this. If the moment goes like this, that means the shear must go like this, and to balance it, the shear must go like this. Then we're done. Pretty straightforward, right? So the interesting part is this. You see, the buckling of the column member, which is the BC member here, really depends on the direction of bending. If the critical load, the actual force acting on the column member is not P, in the mode 1, actually I forgot to write here, right? Now we're going to say, so please complete this part. So we should say that consider mode 2 buckling. So the first one is mode 1, the second one is mode 2. This should be step 2. Here, this is mode 1, and the other one is mode 2. The actual force or the effective force acting on the BC as a column member in mode 1 is P minus V, is this value. But in mode 2 is P plus V. Therefore, when we combine them together, the load deflection curve, of course, depending on which direction you want to use, it's going to be look like this. Let's look at the P minus V part. Why in the P minus V, the curve will go up, not go down? This is the important conceptual question. Why is that?
Because V is negative.
And the math, if it's not clear to you, use this. You're gonna use the mathematics to help you to think. You're gonna let P minus V to be your critical load, right? Now, in order to fail the structure, what you need to worry about is the amount of force, which is external force P. Therefore, in this case, the force you can apply in order to buckle it equals to PCR plus V. So that's why it's going to increase. Make sense? And vice versa. So this is in mode 1. Now in mode 2, you have P plus V equals PCR. What's PCR? PCR is the inherent property that has something to do with the column, with the materials, with the length, with the geometry, with the boundary condition. But in this case, we are not changing boundary conditions, so everything is pretty much the same. In order to fail this column in the mode 2, P will have to be PCR minus V. So the actual value you applied to this column is actually reducing after buckling. So that's why in mode 2, we have this. Mode 2 is going to be going up and goes down like this. And mode 1 is going to be going up and then keeps going up like this. So this is mode 1 and the other one is mode 2. Mode 1 here and mode 2 here.